All right, welcome everyone to Neuro-Symbolic Wednesdays. This is our first talk of the series. Okay, so today we have Abu, and you'll see him appear from time to time in our series slash summer schools, and he's doing lots of work analyzing exactly the extent to which LLMs reason. So you hear all about that today. We thought this was a good way to kick things off because there's a confusion around this issue. How is it that in neurosymbolic AI we're calling for reasoning, and yet there seems to be reasoning going on in LLMs? So, all right, and I'll just announce real quick what the next one will be. So we're going to follow up on this with taking a close look at exactly how these reasoning models are trained, including the DeepSeek paper, which had a big influence. So we'll be going over that paper as well as sort of recent ways people look at training these models. Okay, with that, take it away, Abu.
Thank you so much, Alex. Yeah, I kind of wanted to talk today about some work that I've been doing over the past few years, kind of more carefully examining language models and basically just asking the question: can they learn to reason? And if not, then can future language models, learn to reason? With further development, or can they learn to reason better? With maybe increasing scale. So basically, if you've seen headlines, over the past 2 years, a lot of them have become very optimistic about language models' ability to reason. Right? Microsoft says new AI shows signs of human reasoning. Right? The GPT-4 paper was, titled "Sparks of AGI," right? Artificial general intelligence. Some glimpse AGI in ChatGPT, others call it a mirage, right? AI has evolved to reason like humans, scientists say. Right? These are pretty bold claims. And it's supported a lot by some benchmarks, right? ChatGPT performing at or above the median performance of, several 100,000 test takers on the MCAT exam, which is the entrance exam for medical school. Right, you have OpenAI's own benchmarks being done on the LSAT. Right, the LSAT is the exam for studying law. Right, and the results are seemingly very impressive. It's like the 88th percentile, right, as compared to human test takers. NYU Langone, which is a large hospital network in New York, using GPT-4. Cleveland Clinic, Baptist Health started to use GPT-4. So based on these headlines and these results, I mean, it seems that language models are now capable of practicing medicine or law, right? So, but at the same time, you have other kinds of more careful studies. Language models are susceptible to incorrect patient self-diagnosis in medical applications, right? ChatGPT misdiagnosed most pediatric cases. GPT-5 is launched, but the AI clearly is neither AGI or artificial superintelligence. And even Sam Altman himself is more recently kind of taking a more a toned down approach, where he's acknowledging that there might be a bubble in the current the market in AI, and that GPT-5 is also for a lot of people doesn't really fit the definition of AGI. So the main questions that I want to kind of address in this talk is: can current language models reason, and can future language models reason? So the first question, can current language models reason? I want to talk about chain of thought prompting first, because that's kind of like what led to the initial kind of suspicion that language models might have some at least non-zero reasoning capability, right? Because prior to chain of thought prompting, people were using largely what's called direct prompting, where if you give the model a question, let me turn on my highlighter real quick. Okay, there we go. You give the model a question, and then you just ask for the answer directly, and you hopefully the model will give you the right answer, right? Whereas if instead you give the model a question and you ask for some sort of chain of thought, such as from this trigger phrase like "let's think step by step," the model will actually do some reasoning, and then at the end give you some answer. And empirically, people have found that chain of thought prompting had significantly improved the performance of language models on a lot of reasoning tasks. But there are many potential confounders in these benchmarks, that test language model reasoning using chain of thought prompting. The first being data contamination, right? Do these benchmarks measure reasoning or retrieval ability? For example, a benchmark may ask the model to deduce some kind of fact, but it already knows that fact from pre-training somehow. Another possibility could be poor out-of-distribution generalization, right? The model may rely on shortcuts or heuristics or spurious correlations that may have worked well for the examples from the training distribution, but don't really generalize to examples outside of that distribution. The other thing that we want to kind of do is, when people measure the accuracy of, the performance of language models in these kinds of studies and these kinds of benchmarks, they focus on the label accuracy, which is shown here, right? But instead, we kind of were curious, okay, what happens if we more carefully parse each of the steps, and can we evaluate the correctness of each step, right? That'll give us kind of a better analysis of or understanding of how the model is actually performing the kind of the proof or the search to find the answer. So the overall idea here is basically doing some sort of formal analysis of chain of thought to more precisely and systematically measure the reasoning ability of LLMs. Oops, there we go. To do so, we formally analyze their particular chain of thought. And we do this in a few steps, the first being to parse each sentence from the chain of thought into a logical form. Right. So for example, I have this simple chain of thought: Alex is a cat, all cats are mammals, Alex is a mammal. Right. And I can parse each of these sentences into a simple logical form here in first order logic. Right. Cat of Alex is true for all x. If cat of x, then mammal of x is true. Right. And then mammal of Alex is true. Right. And then I can check whether each logical form is then deducible from previous logical forms via some rule of deduction or some inference rule, right? And that allowed me to essentially reconstruct a proof, right? Given, cat of Alex is true, and for all x, cat of x, mammal of x is true, I can conclude that mammal of Alex must be true. So a simple example of modus ponens here. But if we want to do this to the actual, chain of thought sentences from a language model, right? We need to have some sort of question answering data set where the sentences are simple to parse, right? And convert into first order logic. And ideally, this data set should also allow us to control for all of the confounding variables that I had mentioned on the last slide. And so to this end, we introduced a new data set called Pronto QA, which is short for Proof and Ontology Generated Question Answering Data Set. And I detail it in, there are two papers we describe it in ICLR 2023 and in Neuro 2024. So if you want to read more about those, about the details, please refer to those papers. But one important aspect of quantum QA is that it's synthetic, and we do this because we want to better control the data. It also allows us to directly address the question, the issue of data contamination, right? Synthetic examples are not in the training data of these models, right? And so it makes it much easier to generate examples that we know the model hasn't seen, right? Or that it has not contaminated training data. So we generate these examples using a fairly simple process. Basically, for each example, we first generate some sort of graph, right? And this graph you can think of as, it could be an ontology where you have things like, different types of objects with different properties, right? These edges kind of denote like a subtype or subset relation here. And we convert the graph into the body of a question, right? Basically, for each edge in this graph, we generate a sentence. And so, going top down here, we can generate sentences like each animal is multicellular, every animal is not unicellular, vertebrates are animals, all mammals are vertebrates, mammals are furry, mammals are warm-blooded, and so on. You can see I'm just kind of, descending this tree structure edge by edge and outputting a sentence for each edge. So then we generate the question, and we do so by first performing a random walk for k hops. So let's say we pick randomly to start from cat and then go up the tree or the graph and stop after doing some number of hops, right? Each hop basically corresponds to a reasoning step. For each step in the walk, oops, there we go. So for each step in the walk, we generate a chain of thought sentence, right? Alex is a cat. Every cat is a feline. Alex is a feline. All felines are carnivores, right? We're just walking up this path until we get to the end, which is Alex is warm-blooded. And then we generate a query from the first and last node in the walk, right? We see starting with Alex is a cat, we say true or false, is Alex warm-blooded? And this is the just fully generated example, which contains the body of the question, the prompt here, the query, as well as the chain of thought. Right? We kind of just put all the pieces together. And so to test how much the model actually relies on knowledge acquired from pre-training rather than performing reasoning, we generate three types of ontologies, or three types of graphs, right? There are true graphs, or true ontologies, which contain facts that are consistent with the real world, facts like all cats are mammals. But we also kind of are curious to see what how the model would reason if given graphs that contain false facts, like all mammals are cats, right? And then finally, we also were curious to test model reasoning capability whenever the graph has facts that are neither consistent or inconsistent, right? So in this case, we replace the words of the noun, the concept names, with kind of fictional names, like all bumpuses are bumpuses, right? We also add distractor sentences to prevent cheating. Try to make the examples kind of robust against heuristics. But to keep in mind, I think it's important that since we formally analyze the model chain of thought, it's more difficult for the model to kind of cheat, since it has to kind of show its work in a sense. And I want to say that it's important that we use few-shot prompting to kind of encourage the model to generate easily parsable chain of thought sentences, right? Otherwise, it might generate its own kind of open-ended chain of thought, which might be more difficult to parse into first-order logic. And here's kind of a high-level overview of the first set of experiments that we ran. where we see the proof accuracy. So this is the correctness of the entire proof, right, in the chain of thought. And we evaluate it, versus different sizes of models. In this case, we're looking at GPT-3 models. And we can see actually that larger models are just better at reasoning than small models in terms of the accuracy of the proofs that they generate. And so let's just focus on the largest model, henceforth. Real-world knowledge also helps reasoning, it seems, right? You have these different kinds of ontologies: the fictional, the false, and the true ontology. We see the model with the fictional ontology achieve, not that impressive accuracy. It's not that far from random chance, which is 50%, and the same thing with false ontologies too. It's interesting that the gap between the two is actually not that far off. And yet the model's performance is significantly better if you use a true ontology, right? Which means that it's kind of exploiting the fact that it's learned a lot of stuff about the world from its pre-training to kind of improve its reasoning performance, right? Which is a bit problematic, because that means that it's essentially cheating to do well on the questions that are generated with the true ontology. Okay, and also longer proofs are still challenging, right? If you look at 1-hop versus 3-hop versus 5-hop questions, the accuracy just seems to drop, right? But this is, keep in mind, this was with GPT-3, so models have changed quite a bit since then, and I'll get to that later in this talk. So I think one big question that we're kind of curious about answering is how did language models actually reason step by step, right? We've only looked at kind of the overall proof accuracy so far. And so to answer this question, we will look at breaking down each step and categorizing their errors. And so the first type of error in a proof step we will define is what's called an invalid step. And this is pretty straightforward. Basically the conclusion doesn't follow from the premises. 4 is an integer, all primes are integers, therefore 4 is prime is an invalid step, right? The other kind of step that we want to consider is what's called a misleading step, right? So here, let's say our goal is to prove that Alex is warm-blooded, and we've proved so far that Alex is a mammal, right? Ideally, we want to use the fact that all mammals are warm-blooded to then conclude that Alex is warm-blooded, right? But if instead we said that, since all mammals are vertebrates, therefore Alex is a vertebrate, that doesn't help, right? Because not all vertebrates are warm-blooded, and so it's kind of like leading us in the wrong direction. We took a wrong turn, at a fork in the graph, right? And we're kind of moving away from the goal. And that's why we call it a misleading step. So I see. Okay, so questions will be asked at the end. Got it. So if we actually break down each of these kind of bars into little, sub-bar plots, by categorizing each of the kinds of steps, right? So this dark red bar here basically indicates the proportion of incorrect proofs that contain a misleading step, right? And this dark red bar here is a proportion of incorrect proofs that contain invalid steps, right? And these dark blue bars actually indicate the proportion of correct proofs that contain misleading steps, as well as invalid steps. Right, so we can see actually that the model, even though it does sometimes make mistakes, when it does have a correct proof, it's able to occasionally recover, right, and maybe resume the search and find the correct answer. But we also see that for the cases where the model gets it wrong, there are a lot of instances where there are misleading steps and invalid steps, right? And so the question becomes, so what is the cause for the model's failure to answer the question? Is it the misleading steps or the invalid steps, right? Or is it something else? Right, so most incorrect proofs contain a misleading step or an invalid step. And so we kind of further break down kind of the analysis by looking at here we're plotting the proportion of incorrect proofs where each step type is the first type of error that the model makes in that incorrect proof, right? So this green bar here represents the proportion of incorrect proofs where the first mistake is a misleading step, right? And this red bar is the proportion of incorrect proofs where the first mistake is an invalid step, right? And so as you can see, like the smaller models, it tends to be that the invalid steps are the most common first mistake, right? But as the model size gets larger and as you improve the training by doing instruction tuning, right? The likelihood that the first error is an invalid step decreases, right? This red bar kind of shrinks, and instead this green bar grows, right? So this suggests that actually the model is the most common, reason for the model getting sidetracked and making a mistake and getting the final answer incorrect is due to the misleading steps. It kind of, is not able to find the right path to the goal, despite actually being able to find, correctly take steps, right? Correctly perform kind of valid steps of deduction, right? And so that kind of leads us to conclude that actually the models are pretty good at making valid deduction steps, but what they're really having trouble with is proof planning, right? This kind of proof search task, right? In order to find the conclusion given some premise. And so this suggests kind of a more fundamental limitation to the model's ability to search. And this is what we're going to focus on in the subsequent parts of this talk. So this was back in GPT-3, right? Back in 2022 and 2023. Last year we've seen the development of what are called reasoning models. And I believe Asim will talk more about these next week. But just kind of a high-level overview, language models, when they're post-trained with reinforcement learning algorithms such as PPO or GRPO, they have significantly improved performance on reasoning tasks, right, including on Pronto QA. And so you can see this kind of benchmark. This is from the DeepSeek R1 paper, where DeepSeek R1 is this model that has been trained with reinforcement learning, right? And same thing with OpenAI. These also have been trained with reinforcement learning. And these are being compared to the models here on the left side, which have not been trained with reinforcement learning. These are kind of the more vanilla LLM architectures. But you can see like a clear jump in performance in some of these benchmarks, right? So simple QA, 28% goes up to 47% for OpenAI A1. Alpaca Eval 2.0 goes from 52 to 87.6%. Right? Coding also sees significant improvements. Live code bench from 38.9, 36.2 to 65.9. Right? So you see these pretty kind of marked increases in performance on these reasoning benchmarks. And so kind of the natural question arises, does this mean RL has solved, language models' shortcoming in search? A recent Apple paper I probably have seen, Shojay et al. In 2025, has showed that actually these large reasoning models, they may not generalize to more complex problems, right? And in fact, if you actually have some sort of task. This is, I believe, the Tower of Hanoi task, where essentially you're given some sort of state that describes a bunch of 3 pegs and a bunch of blocks that are stacked in order on one peg, and the goal is to move the block such that you have the blocks stacked in a different order. I'm sorry, in the same order but on a different peg. So you see the target state here, right? And what you can do is you can actually increase the number of blocks to kind of control the complexity of this task. They call them disks here, but you can see that as you increase the number of disks, Cloud 3.7 Sonnet, this is the non-reasoning model, right? It seems to have difficulty starting around 4 disks. But the reasoning model, if you add this plus thinking kind of flag to the model, it actually performs well all the way up to around 8 disks. But after 8 disks, it also kind of begins to deteriorate in performance, and it performs just as well as the non-reasoning model. And it's interesting, they also found that kind of the number of tokens that the model generates. So the model, these large reasoning models, they will produce very long chains of thought, right? And this is kind of the idea of taking advantage of test time compute, right? Producing longer and longer chains of thought tends to increase the accuracy of the model. And so you'd imagine that as you increase the complexity of the input problem, the number of thinking tokens, they call it, the number of tokens in the chain of thought will increase as well. And that's true up to a certain point, it seems. In this paper, the authors found that after reaching some sort of threshold, the number of tokens in the chain of thought seems to kind of level off. Right. But there are some flaws with their methodology. Notably, some tasks, including the Tower of Hanoi task, they require exponential steps to solve, right, in the tasks that they investigate the models with. Right. And also the number of generated tokens may have exceeded the context limit, right? So it's possible that that may be the limiting factor, right? That maybe just because these tasks require exponential steps to solve, then if your chain of thought needs to be exponentially long, right, then it may have reached the limit in terms of the number of maximum tokens the model can see. And that might be kind of adding some sort of unfair limitation, perhaps, on the model. So to address these kinds of potential confounders, we extend Pronto QA to create or to generate very, very large graphs. And we will measure complexity using a metric that we call look ahead. And so this look ahead we define as follows. Let's say we have a graph, a start vertex and a goal vertex. The look ahead is the number of breadth first search steps, or BFS steps, that we need to find the goal from the start vertex. And we also consider complexity with respect to the number of branches, right? And this is kind of more straightforward, which is how many vertices is the start vertex connected to? Okay. So we test large reasoning models on 2 tasks. First, given a graph with a start and a goal node, we want the model to predict the path between them. Right, and it could be any path, just so long as it's a valid path. Although I believe in this data set, we've kind of guaranteed that the generation process will generate graphs with only one path between the start and the goal vertex. So it looks maybe something like this. You have some sort of graph, you give the graph as a set of edges to the model, and then you ask the model for the path between the start and the goal. The second task is, given a natural language reasoning problem, such as the one over here, starting premise, in this case, Phe is INESAM, and some goal conclusion. We want to prove that Phe is DETMI. The next step in the proof is blank. We want to predict the next step in this proof. Right, so this is kind of a bit easier of a task at least in the graph search setting, because you only want to predict one vertex as opposed to a full path. But at the same time, this is kind of phrased as kind of a natural language reasoning task as opposed to a graph search task. So it's possible the model may perform differently, either better or worse, when working with natural language versus a more symbolic representation. Right, and this kind of example is equivalent if you map each of these kind of clauses to a vertex. It's kind of equivalent to the topology of this graph, where each edge represents kind of a if A then B fact in the question. So unlike tasks like Tower of Hanoi, these tasks that we define can be solved in linear time. You just have to search, linear in the number of vertices or edges. And at the same time, only a linear number of thinking tokens are needed, right? So that means it shouldn't have any issues where the model kind of reaches the limit on the number of tokens that it can generate or that it can see. And we call this new data set the deep reasoning data set, or deep RD data set. And you can read more about it in our archive paper if you'd like. And here are the basic results. We look at graphs with different numbers of branches, meaning the start vertex has a different number of child vertices, right? We also plot the accuracy of different models. This is DeepSeek V3, DeepSeek R1. So V3 is kind of a non-reasoning model. R1 and O3 and O3 Mini are reasoning models. 4.0 is OpenAI is a non-reasoning model. And you can kind of see that they do perform the worst as compared to the reasoning models here. But the reasoning models, you can see in the red and orange curves, they perform pretty well, but only up to a certain look ahead, it seems, right? So about around 64 to 100 is when you see this kind of drop off in their accuracy as well. Right, so this kind of corroborates what was seen in that Apple paper. Yeah, despite our task being solvable in linear time, and beyond a certain size of graph, it seems that all models, regardless of how much reasoning they do, struggle on this task. And if you look at the purple lines here, we kind of limited the experiments there because it was just so expensive to run a lot of experiments. So we just picked kind of like 2 points in the middle here to run those experiments. And we also find that O3 struggles similarly as compared to the other models. And so this was in the graph search task, right, where the input, the graph is given like symbolically, and the model has to output a sequence of vertex IDs. But in the natural language proof search task, where the model just has to output the next proof step, you see kind of very similar behavior, except now the accuracy of random guessing is 50% in this plot, which is kind of why you see these models kind of hover around 50% after a certain look ahead, right? In this plot, it becomes 25%, right? Because the random guessing accuracy would just be picking one of the 4 children of the starting vertex, right, as the next step. And here the random guessing accuracy is 1/8, and so on. What's interesting is actually we also ran an experiment where we set the number of branches to be equal to 1, which means that actually there's only one chain of vertices in the graph, and there's no other branches coming out of it, which is kind of an interesting study, because now the model doesn't actually have to do any searching to solve this, right? It just has to kind of follow the list of vertices to get from the start vertex to the goal vertex. And yet, even in this case, we see that like after around 400, 500 vertices, the model's accuracy in this task, goes down. And this could be due to the fact that, the model has to kind of like do some sort of pointer following and very accurately copy the pointers from the input, the prompt, into its output, right? And if the model has some small probability of making a mistake anywhere in this process, then as the number of edges grows, then you find that the probability of an error will also grow exponentially, which would kind of explain this result potentially. And the other thing that we also kept track of was the average number of tokens that the model produced in its output. And we see kind of a very similar, pattern as in the Apple paper, right? Where, initially the reasoning models began by generating increasing number of tokens with increasing with increasing problem complexity, right? At least for the reasoning models, right? The orange and the red curves and the purple curve as well. But then after some kind of point around 64 look ahead, it seems here, they stop generating more tokens. They kind of like flatten out and level off, and really only generate about like 5,000 to 10,000 tokens. O3 generates more. It's a more expensive to run, but evidently it doesn't really help O3 perform any more accurately. So why do language models and reasoning models fail to generalize? Well, we hypothesize that LRMs are limited by the underlying architecture, the transformer architecture, which tends to overfit to its training distribution, right? And that can lead to poor out-of-distribution generalization. So to get a sense of the complexities of graphs and proofs in the training data of these models, we actually chose to analyze a bunch of graphs from several public data sets. And we also analyzed the proofs from the natural proofs data set, which basically just contains a lot of kind of human written proofs. We then computed the look ahead and the number of branches of each example in these data sets, right, and visualized them in histograms. And this is the result of this visualization, where you can see the different columns are different data sets, different graph data sets. This last column is the natural proofs data set. The first row is a plot of look aheads, whereas the second row is the plot of the number of branches. And it would make sense because that the proofs doesn't really have this notion of branches, because in natural proofs you have more complex proofs with kind of universal quantified rules, in which case the number of branches is kind of potentially infinite. If you have something like for all x, f of x is true, I can substitute anything for x to get a true statement, f of a or f of b or f of c and so on. And so the number of branches of that node is effectively infinite. And so that's why we kind of don't compute the number of branches here for natural proofs. These red lines indicate the 50th, 75th, 90th, 99th, and 99.9th percentiles, respectively. And you can see pretty clearly that actually all of these distributions of kind of graphs with different complexities, they're all very heavily concentrated at very simple graphs, right? These look aheads are almost always below 100. It's pretty clear that the vast majority of training examples in these data sets, they're quite simple. They're not very complex. Their look aheads are fairly small, right? So in a separate study, we also asked LRMs to solve synthetically generated math word problems, right? We used kind of a very interesting logic programming approach to generate these problems, which you can read more about in our paper. For each example, we compared the length of the LRM output to that of the shortest proof, right? We basically converted the shortest proof into natural language, measured the number of tokens of that, and then compared that to the number of tokens of the model's output when it tries to answer the questions, right? And we plotted these lengths in a histogram again. And we see that, so this blue histogram is the distribution of the lengths of the shortest proof, whereas the orange histogram is a distribution of lengths of the model's predictions, the model's output, right? And you can see that the model generates many, many more tokens typically than the shortest proof. Although sometimes for QWQ, you see, that it aligns fairly well with the shortest proof distribution, but only for problems that it gets correct. You can see kind of like this very large tail of it looks like a kind of a diffuse background of problems where the model's output is significantly longer than the shortest proofs. Right. So as a result, we found that these models are kind of very inefficient in their thinking, and we kind of observed that as well in in our graph search experiments from before. So next, I want to talk about whether future language models can reason, right? And I want to dive into this from the perspective of scaling laws, right? So if I have some language model, I train it on the simple next word prediction task, right? The language modeling objective, and I plot the loss function as a function of time or the amount of training compute. You'll see that it begins to drop off, at some point, and then after a certain amount of training, the loss then kind of levels off, right? It stops decreasing quickly. But if I increase the size of the model, the number of parameters, right, I see that as I run training, this point where it kind of levels off, where it stops decreasing quickly, happens a bit later, but also at a bit lower of a loss, right? So that means that this trained model, it took a little bit more time to train, but it learned to perform better. It achieved a lower loss function, right? And as I further increase the number of parameters, I see that this trend continues very predictably, actually, that each model takes longer to train. It takes more compute to train, more data to train. But each model also learns a better kind of target model as well, right? Where it's able to achieve a lower test loss. And this was from the Kaplan et al. Paper from January 2020, right? And Microsoft saw this essentially as, a green light to invest heavily in scaling up this kind of approach and throwing compute at the problem, right? And they invested heavily in OpenAI, and they used that investment to train GPT-3, which was released just a few months later. So earlier scaling laws looked at what's called the next word prediction task, or the language modeling task, right? And we saw this kind of very neat pattern in that task, in the loss function for that task. But what if we run the same experiments with a search task, right? So that would allow us to essentially, figure out whether increasing the scale of these models will actually make them better at search. And so here is kind of an example of an input to a transformer that we will train, where we have just basically a list of edges. These are like special edge separator tokens. And then in between them, you have kind of these edges that 4 connected to 1, 8 connected to 3, 3 connected to 6, and so on. And then we have this query token, right? This query tokens, I should say. This is the start vertex, the goal vertex, and then our current vertex is at the very end. And the task of the model is to output the label of the next vertex along the path from the start to the goal vertex. In this case, it will be 3. And in these experiments, we're going to vary the size of the model in terms of number of parameters, as well as the complexity of the graphs, the number of vertices. And so here is kind of a plot showing different training runs. So where we have different models of different sizes, right? So the light green runs are shown here. We run 4 different training runs with different seeds, just to see if there's any randomness in the initialization or the ordering of the data, right? And we do see there is actually quite a lot of variance. But you'll note actually that there is no discernible pattern with respect to the actual model size, right? It doesn't seem like having larger models is helping the model to learn this task, this graph search task, any more quickly. If instead, however, we kind of vary the complexity of the graph, here we change the graph size, right, going from 9 all the way to 49 vertices, you see that it gets progressively more and more difficult, this very clear pattern, to learn how to perform search on larger graphs. And if you were to kind of plot, the minimum test loss that it achieves after, a very large amount of training, as a function of the size of the graph, you see this kind of, trend that it just takes more and more. I should say, the model becomes worse and worse at performing the task as the size of the graph increases. But what if we allow the transformer to output intermediate steps, such as in chain of thought, right? And so what we do is we try to train these transformers to perform depth-first search. And so the input will look a little bit different, where now we have kind of a sequence of vertices that the model has visited so far. So in this case, the model visited 4, then 1, and now it has to go back and visit 3, right? And then hopefully 6. And we see here, this is the train loss shown on the left side, the test loss on the right side. And again, as you increase the size of the graphs, the complexity of the graphs, the loss function, both for the training and the test, increases, right? Which means that it gets more and more difficult to perform depth-first search for larger graphs. At the same time, though, if you increase the size of the models, the transformers being trained, you don't see a very clear pattern that suggests that larger models learn faster, right? In fact, it seems actually that the smaller models learn faster than the larger ones for this task. So we aim to find empirical scaling laws for language models on graph search. And we found that larger language models are actually not better at learning how to search. And it becomes increasingly difficult to learn how to search on larger graphs, even with better prompting, such as chain of thought or depth-first search, right? And perhaps this inability to search, has led to this kind of plateau of AI capability. But maybe not. And I'll show you some reasons for why this may not be the case. And this kind of stems from our exploration into the question of whether transformers actually learn some sort of generalizable search algorithm. Because there were some training runs from the previous experiments where the model did learn how to search over graphs with very high accuracy. And so to answer this question, we apply what's called a mechanistic interpretability analysis to the models trained on the earlier experiments, right? The goal of this interpretation, this mechanistic interpretation, is to effectively kind of reverse engineer the algorithm that the model has learned to perform the task. We focus on models trained on intermediate size graphs that achieve better than 99.5% training and test accuracy. And for the sake of time, I'll skip the details of the methodology, but if you want to learn more about how we actually uncover this algorithm, procedurally, I urge you to read the section in the Eichler paper. So what does this algorithm look like? The algorithm that the model has actually learned to perform search. Well, suppose we have this kind of fairly simple chain graph going from 0 to 9, where 0 is the start vertex, 9 is goal vertex. In the very first layer of the transformer, we find that the token for 1, this vertex 1, it stores the representation for itself, which makes sense because this is the first layer. The model hasn't done anything, right? The token for 2 stores information about itself, the vertex 2, right? It doesn't store information about other vertices, at least not yet. But what we find is that in the second layer input, the token for 1 seems to attend to the token for 2, right? And therefore, it copies representation of this vertex 2 into the token for 1. So now the token for 1 stores, within it the representation for both vertices 1 and 2. And then the model seems to do essentially the same thing, right? Layer by layer. In layer 3, or I should say in the second layer, vertex 1 attends to vertex 2 again, but now vertex 2 contains the representation for both vertices 2 and 3, right? And therefore, after layer 2, at the beginning of layer 3, the token for 1 now stores representations for vertices 1, 2, and 3, right? And this seems to happen at every vertex in the model. And eventually, if you just repeat this process where you're kind of repeatedly copying the vertex that this set of vertices are connected to, right? This set of 1, 2, 3 is connected to 3, right? So we copy from 3 into 1, and then now 1 stores representations for vertices 1 through 5, right? And so it seems that the model is effectively computing what are the sets of vertices that are reachable from each vertex. What's more is actually this algorithm, what we call this path merging algorithm, is actually quite efficient, right? It does this search in parallel, from every vertex simultaneously. And therefore, it can actually compute the set of reachable vertices in exponentially quickly, meaning the size of the set grows exponentially with the number of layers, right? So this is actually a very kind of robust and very interesting, and it's a real search algorithm that people have developed for like parallel computing environments. So even if the model does struggle to learn this, the transformer struggles to learn this algorithm for very large graphs, it is able to learn this algorithm for kind of intermediate sized and small graphs. So this suggests that maybe even if scaling alone doesn't address the language model's inability to perform search, maybe new training methods may do so, right? We have some preliminary results actually showing that techniques such as curriculum learning can be used to train LLMs to perform depth first search on arbitrarily large graphs. And so basically what curriculum learning entails is you first start by training the model on small graphs, right? And then progressively increase the complexity of the graphs. So you wait until the accuracy reaches some threshold, right? And then you increase the complexity of the training set by adding slightly larger graphs, right? And then you again wait until the accuracy reaches the same threshold, right? And then you add even more large graphs. And then you continue this process until eventually the model has learned how to search over all of the graphs in your data set. We also found that using reinforcement learning can be used to teach LLMs how to search on arbitrarily large graphs, but with the caveat that the training data contains the examples of the large graphs, right? For example, we found that these models do still struggle in OOD generalization, right? So they can't really learn how to search on graphs that are much larger than what they see during training, even if we use RL or curriculum learning. But these results are kind of so preliminary, we haven't published them yet. But all of this goes to kind of suggest that, even though scale alone might not, lead to LLMs and LRMs that can perform search and reasoning robustly, new training techniques might help. New approaches might kind of help develop models that are better at performing search. Okay, yeah, and I want to thank you guys for listening, and I want to thank all my collaborators, of which there are quite a few, but I showed them here, at least for the papers that I discussed in this presentation. Yeah, and I'd be happy to take questions now.
All right, great. Thanks, Abu. Olga. Okay, there we go. Do you want to share the wrap-up slides?
Sure. Yeah, so again, here just a reminder, like not a reminder, but like overview what we just heard from Abu. Here is his information. If you would like to take a look at the links, like Abu's website, Scholar Google. Okay, hope you're done with that. So for the next week, bring your popcorn. We are going to have Asim Manwar from IBM. He will be speaking about training large reasoning models. And also, if you'd like to join us, here is a bunch of ways how you can do it: Discord, GitHub, YouTube, LinkedIn, our learning site, and you can participate in our communities. Yeah,
Great.
so hope you're done with.
Yeah, and just so now we'll go to questions. So, and there are a bunch of questions on Discord. So if you didn't know it already, go to Discord to ask questions. Look for the Neuro-Symbolic Wednesdays channel. Okay, and we already have a bunch of questions there. So Olga will read the questions, and then once we're done with those, unless they keep coming, Olga may have some questions. I have some questions, and we're leaving half an hour, so we're experimenting with this format, and if we have way more, we'll make it longer, or if we have less, we'll make it shorter in the future. But the purpose is a deep dive. So also on the Discord channel are the papers that Abu gave for background reading. So it's also fair game to ask any questions from his papers. Okay, so all right, with that, take it away, Olga.
Okay, we have a bunch of questions. I hope I start with the first one in the beginning. Maybe some of the questions are about particular slide shown at the moment, so we'll try to guess about which slide. But okay, the first question we have, perhaps a bit of a naive question. Why is it that for LRMs, with increasing the complexity, the number of tokens does not keep increasing and hits a threshold? Is that a generic phenomenon?
Yeah, that's a good question. Let me actually go to that slide real quick. Let me not present and just show you the PowerPoint. Let me share my screen. Window. Yeah, this one is fine. Okay, can you guys see this? Okay.
Yeah. Thank you.
Okay, great. Yeah, so this is basically the kind of plot that they're referring to. So that's a good question, actually. I don't think I think the reason why these models don't actually further increase their tokens is because their training doesn't really contain examples that are much larger than this 64 to 100 range, right? So their training distribution, even during RL, they probably don't see examples of problems that are more complex than that kind of threshold, and as a result, they probably don't even learn to kind of spend more time to reason and try to get it correct. So, and I'm actually not entirely sure why the kind of the thinking process doesn't continue if it actually can't find the actual path, right? It might just give up, or it might have actually. One interesting thing that could be happening is that it convinces itself that something else is the right answer, right? After a certain number of tokens, right? Maybe some sort of hallucination is happening. These are very interesting questions, and I think it deserves a more careful study of an analysis of the actual output of these reasoning models, these chain of thought tokens, to see what are the mistakes the model is making, especially for these larger graphs. And we have some preliminary analysis in our paper in this paper on arXiv. Toward the end of that, we have some kind of insights there, but it's very kind of surface level, and definitely a lot more work can be done to do a much more careful and systematic analysis. Yeah, but that's a good question.
Okay, thank you. The next question is a question about the fictional false true ontologies.
Yes.
Have you done any tests on human subjects with the same data? Current consensus in cognitive science is that humans are actually context-dependent reasoners. So it might be a bit harsh to penalize LLMs for not doing well on tasks that we are not that good at either.
Yeah, that's a good question. But I mean, like, these are actually very simple. So this experiment is from the Pronto QA paper, which is from 2023, 2022, really. But these examples are quite simple. They're only 5 hops. And so if you gave any human enough of an incentive to get it correct, I'm almost certain that they'll get it 100% right. Because these are not that long. I mean, if you ask me the same question about, the examples here in like these very large graph search tasks, then I would say, it's possible that that humans could maybe miss one edge, right, or accidentally connect two vertices together that don't appear together, just because the graphs are so much larger. They have hundreds or thousands of vertices, right? But the graphs in these experiments are very, very small. They're like, tens of vertices, if that, right? So I would be pretty confident that humans can get it perfectly correct given enough of an incentive, like if you pay them.
Mm-hmm. Thank you. Okay, I think a couple more questions that I missed in the beginning. These were probably about, like, from the beginning of your presentation, how did you construct the data set? And another question from the same person. Okay, actually, that's a maybe related question. How about when a word has multiple meanings? For example, riverbank and cash bank.
Oh, yeah, that's a good question. So we chose kind of words here, at least in the true ontologies, that tend to be fairly unambiguous, especially given the context. So we didn't actually consider words with multiple meanings. And in the fictional context, we made sure that each of these vertices, was assigned like a unique fictional word, right? So there is no confusion. If like the model sees a word, it will know exactly which vertex that it refers to. There are no like two vertices with the same label. And the way in which we constructed this data set was, kind of described here, where first we generate a graph. It looks like this, and then for every edge in this graph, we convert it into a sentence. So you can do this either like traversing the tree top down or bottom up, or it doesn't really matter, right? Yeah. So this edge here, animal goes to multicellular, gets turned into the sentence. Each animal is multicellular, right? This edge going from vertebrate to animal goes to vertebrates or animals, right? And so on and so forth. You do this for the full example. And then what we do is we then do a random walk from some vertex, let's say cat, to warm-blooded, right? And then this random walk tells us what the chain of thought should look like, right? Starting with Alex as a cat, I can conclude that Alex is a feline because every cat is a feline, right? And then so on and so forth. I continue the walk until I get to the goal, which is Alex is warm-blooded, right? Mm-hmm. And then I can take the start vertex and the end vertex of this walk to get the query. Alex is a cat, true or false, Alex is warm-blooded. And then I just combine all of it together to get the full example here.
And while we are on this slide, I actually have a question from myself. Sure. How do you construct these through ontology?
Yeah, that's a good question.
Manual construction, or do you automatically extract it, I don't know, from Wikidata, or like, yeah. So regarding the true one, and how do you kind of break it to create a false one?
Yeah, that's a very good question. So what we do is we just manually constructed it. We constructed 3 different ontologies, one about animals, one about numbers, and I forget what the third one was about. It might have been about insects, I think. But Yeah, we just manually constructed those 3 ontologies and just randomly sampled those when creating each example. For making false ontologies, actually what we do is we create a random tree using kind of the same methodology as a fictional ontology. But we replace each of the concept names with real concept names, right? And so it becomes very, very likely to generate an edge that's not true, like all insects are vertebrates, right? Or all animals are warm-blooded.
Okay, thank you.
I'm honored, by the way, Abu, that your cat is named after me.
Oh, is it?
Just a side note, I think it would be super interesting if, I don't know, you or someone in the world can find a way to build those ontologies, like basically a world model automatically, if we can extract this data from, say, Wikidata. But it's like, yeah, not a question, just a side note.
Yeah, I agree.
Okay, continuing, actually, yeah, a bunch of related questions. Were the models given contexts that the question comes from a fictional or false ontology? How does it compare to when they were not given this information?
Yeah, that's a good question. So I believe in our experiments, we use few-shot prompting. So the in-context examples came from the same distribution, right? So for the false ontology task, all of the in-context examples also were examples from the false ontology, from a false ontology, not from the same false ontology, right? So the model actually has seen examples of, performing correct reasoning with the false ontology. We didn't actually compare to see what happens in the OOD setting, where if you gave in-context examples that were not from the false ontology, how well does the model do with the false ontology, right? And the same thing for the true and the fictional ontologies. That's an interesting experiment that we didn't try, but that'd be interesting to try. It's a good suggestion.
Thank you. Okay, so next question. What is the definition of misleading versus invalid? And how do you categorize that? Are you using human annotation or some sort of automated annotations?
We're using automated annotation here. We do semantic parsing of each of the sentences of the language model's output, right? The chain of thought. We parse them into logical form, and then we can check, does this logical form for 4 is prime, does it follow logically from the premises or the earlier steps, right? And here we can see that actually, no, it doesn't, right? Because this is kind of getting it backwards. Even if all primes are integers, we can't conclude that 4 is prime, right? We can only conclude that some prime number is an integer, right? And so that's how we categorize this invalid step. It's when the conclusion, the logical form, does not follow from earlier logical forms. Misleading steps are, on the other hand, different in the sense that they may follow logically, right? So Alex is a mammal, all mammals are vertebrates, Alex is a vertebrate. That follows logically, right? That's just a valid deduction step. But we find that it's misleading because this edge, this kind of step going from Alex is a mammal to Alex is a vertebrate, is not along the path, the ground truth, the path from the start vertex to the goal vertex, right? So that's how we characterize or just detect misleading steps, is if the edge is not on the path.
Thank you. Okay, next, just a comment. You guys are doing great. Love your sessions. Would love to do my PhD under Abu Saparov supervision. So I suggest that there is no name, but you have Professor Abu Saparov details and contacts. You can maybe message him directly to discuss this. Okay, next question. Should we use LLMs for searching instead of classical graph search algorithms?
Yeah, so that's a good point, because if you look at, for example, this, like if you have the structured form of the graph, then why not use a classical graph search algorithm? That would just be better, because we know that they run very quickly, right? And they're much cheaper to run. But the point of this kind of study was not really to test whether LLMs can replace classical graph search algorithms, but more what happens if you don't have the structured graph input, right? What if you have some sort of like more complex proof planning example, right? This example here is not super complex, right? These sentences, I could do semantic parsing and convert it into a graph, but That's not really the point of this study, because I can easily imagine examples where the sentences become more complicated and semantic parsing is not as easy. Like I can use a like ChatGPT to paraphrase this, for example, right? And then a lot of semantic parsers will then just break. And the other thing is that like this analogy between like these simple reasoning problems and these graphs, it kind of breaks down if you increase the semantic complexity, the semantic richness of these examples, right? So in this example, all sentences or all facts have the form if A then B, right? Or if B then C, right? And so they can map very cleanly to edges in a graph. But what happens if I add conjunction or disjunction? You know, so if I have sentences like if A, then B or C is true, right? Or if A and B is true, then C is true, right? So now this simple graph analogy breaks down. Instead, I have to use what's called a hypergraph, right? A hypergraph where edges can have multiple parents or multiple like target vertices. But I could still, in principle, use some sort of hypergraph search algorithm, which is totally fine. But then the analogy breaks down even further when I add even more, semantic logical connectives or semantic richness, such as negation, right? If A is true, then not B is true, right? Or quantification, right? For all X, if A of X is true, then B of X is true, or there exists an X such that C of X is true, right? Then there's no longer a clear analogy or mapping from those kinds of sentences into some sort of graph structure, right? In which case we're kind of stuck. We have to do the proof search in that kind of form. Yeah, good question.
Okay, thank you. The search algorithm that the LLM learns, why does it not generalize to larger graphs? What is it that causes this loss of generalization?
Yeah, that's a very good question. So it's simply that the model, after some point, you see that it's doing like these kind of merges of paths, right? Layer by layer. Let's say I only trained the graph on paths up to length 5, right? As opposed to 9. Then the model has no incentive or reason to learn this path merge operation at the end, right? And we find that it doesn't. So then, even though it learns how to do this algorithm for paths of length 5, it can't go any further than that, right? And so its performance kind of drops off pretty significantly. If you look at the paper, after paths of length 5, its accuracy goes down to 0 pretty quickly. And so that's kind of why it doesn't really generalize. It overfits to its training data, which is kind of, pretty common observed property of transformers.
Thank you. Next question. Do you evaluate graph complexity in the graph search benchmark only in terms of the number of nodes or also other metrics, for example, approximate branching factors?
Yes, yeah, we use 2 factors actually to kind of measure graph complexity. The first we called look ahead, and the second is number of branches. Look ahead is kind of related to the number of nodes or number of edges in the graph, but more formally, it's meant to act as a more direct measure of the complexity, right, of the search task. It's defined as, if you're given a start vertex, a goal vertex in some graph, the look ahead is the number of BFS steps you need to take, iterations of breadth first search that you need to reach the goal from the start vertex, right? So kind of it's like a minimum number of steps that the model needs to search in order to know what is the next correct step along the path to the goal, right? And then the number of branches is the other kind of metric that we use to quantify complexity, which is basically the number of child vertices from the start vertex, right? So how many kind of paths are available at the start vertex. And this is useful because we see like in the task where the model has to predict the next step correctly, that it gets around like 1/b accuracy, where b is the number of branches. And that's kind of analogous or equivalent to doing random guessing. If you randomly guess one of the next possible vertices, then you'll get it correct with probability 1/p. Yeah, good question.
Okay, thank you. Okay, now a long one. Thanks for the great talk. Could you provide a formal definition of reasoning? Steps, capacities, chain of thought. What are the sufficient, necessarily processes involved in order for us to talk about reasoning? How do we separate reasoning? The usual implication is human reasoning from a mere usage first, second order logic. See the various features of human natural language that formal logic do not capture. Current use of natural language in LLM benchmark is just formal language coated with some syntactic sugar. This would inform how to model benchmarks, to measure it, and reveal potential reasoning imposters. Output that might look like reasoning, but it is not. There is a lot in it, maybe.
Yeah, I don't really understand the question, to be honest. I guess I can start with the first part, which is defining reasoning. I mean, I avoid a definition of reasoning here, but you can. But I will say that in this studies we focus on deductive reasoning, right? Where basically the task is, given some facts that you know to be true previously, I want to, deduce new facts that I know I can conclude to be true based on the old facts, based on the premises, right? And then I can use this to then, define problems or tasks where I have a set of premises or a set of axioms, right? And I want to find a proof, a step-by-step proof where each step is a rule of deduction being applied, right? That go from my axioms or my premises to some goal, sentence or statement, right? And you can formalize this, a number of different ways. Mathematically, people have studied like proof theory for many, many decades, right? And developed what are called like reasoning or deductive systems to kind of formally describe what deductive reasoning means. And you can similarly extend them to other kinds of reasoning too, like inductive or abductive reasoning as well. And it's definitely a very interesting field, proof theory. I definitely recommend people look into it because I think it's just very fascinating in general. I don't remember the other parts of that question. I don't know if there are, if there's anything else that they ask that's important.
I take the essence of the question to mean something like, well, if LLMs are sort of just approximating reasoning to some extent, what is real reasoning? And so what's the conceptual gap?
Yeah, I mean, I think it's what I mentioned. It's like for deductive reasoning, at least, you want to deduce, facts that were previously unknown, but by applying these rules of deduction, these inference rules, you can conclude that they must in fact be true based on what I know from my other facts, what I know to be my premises to be true.
I'd like to paraphrase
that. Yeah, essentially like deriving new knowledge from old knowledge is essentially like a high level way to describe deductive reasoning.
That's good. I'd say something else you embedded in what you said is your real reasoning as considered by, you could say, symbolic AI people or people who study reasoning proper has to do with the application of some inference rules that apply no matter what the depth, for example, no matter which kinds of nodes, or at least if they can apply in an infinite number of scenarios. So as opposed to being depth limited, say, or so on. So that's maybe one answer, kind of contained in what you said, Abu. But I'd also throw out like things like soundness and completeness. There are ways we can say whether a logical reasoner is correct, and in certain senses, those are two we won't get into here, but for another time maybe.
Yeah, that's definitely a good way to put it. I agree.
Okay, thank you. The next question, we have less than 10 questions left, so there is a chance that we can finish on time. Okay, general question. Is overfitting a fundamental feature of any learning process? Could it be uniquely severe in current deep learning? It seems like biological intelligence has an optimization signal towards lower complexity, which the deep learning does not, if model structure is kept constant during training.
Yeah, that's a very good question. I think, yeah, I agree. Like overfitting, at least if you look at learning theory, like machine learning theory, you see that overfitting is a kind of very fundamental problem of any learning system. But you need to have, and then you can combat overfitting by, having some sort of prior or regularization or inductive bias in the model that kind of, favors explanations or solutions that are not so that don't involve memorizing as much of the training data, right? So I think transformers are very, very good at overfitting, as we've seen, right? So these kind of specific deep learning models are quite good at overfitting. Yeah, and I agree, like having some sort of inductive bias or prior to kind of encourage these models to learn a more general solution, as we see that humans do, quite easily. Humans are very good at generalization, right? I think having something like that would potentially improve these models' kind of ability to learn things without overfitting.
Thank you. Do you have an idea of what sort of role the complexity of an ontology plays? Have you considered using or comparing with something really complex, like, for example, research CYC?
Yeah, so we avoided using real data in our experiments because we wanted to avoid the issue of data contamination, right? These language models are trained on like the entire internet, so I would not be surprised if, the resource you mentioned has been included in the training data. But I mean, the data we generated, synthetically, were very, very large, right? We're large enough at least to show that these large reasoning models kind of drop off in accuracy even after like maybe 60 to 100 look ahead, or the kind of the distance from the start to the goal vertex, right? So yeah, we designed our synthetic data generation process to be scalable and be able to generate graphs that are very, very large as well. Yeah.
Thank you. Okay, then apparently a few questions repeat that you have already answered them. Just 2 questions left.
Okay.
Concerning the number of tokens in output threshold, could substitution play a role?
Substitution. I don't think I understand what they mean by substitution.
Yeah.
Yeah, if they could clarify that, maybe. Maybe we can look at the other question first.
Yeah, maybe Prokhor, if you could clarify the question. Okay, so the last one, it's probably a naive question, but in Pronto QA, how are the ontologies connected to the LLM or its chain of thoughts? How is the architecture of the Neuro-Symbolic system? How large are the ontologies? Do they represent the knowledge that the LLM is trained on?
I didn't quite understand all of that. So this is not really a neuro-symbolic system, right? This is just the in Pronto QA, it's the data generation pipeline is to generate kind of examples that look like this, right? So it's essentially a purely symbolic data generation pipeline, right? We're just generating this graph structure. We convert the edges, vertices into sentences, which then form the question and the answer, right? So it's a pretty simple pipeline on its own. So there's no really neural methods happening, at least in the data generation pipeline, right? Yeah, and I don't remember the other parts of that question. Sorry.
Okay, I'm not sure I understand the question. How is the architecture of the Neuro-Symbolic system? I think you mentioned it's not
Yes. Yeah.
How large are the ontologies? Do they represent the knowledge that the LLM is trained in?
Yeah, so the ontologies, we generated them to be like roughly like to have at most 5 hops. So like I forget the exact number, but the number of vertices varies from like 10 to 20 maybe. So they're not actually that large, at least for quantum QA, right? And this is back in the days before large reasoning models, right? When even these small ontologies would cause problems with LLMs. And to answer the other part of the question about how we wanted to see, to investigate whether these ontologies contain information that the models were trained on during training. That's the purpose of having these kinds of 3 different types of ontologies, right? We mentioned it here. So some ontologies are true ontologies, which look like this. They actually represent facts that are true about the real world, and very likely the model has learned these facts as well from the pre-training. But we also generated false ontologies, or false graphs, where we kind of generated randomly, what the tree looks like, and then labeled each of the vertices with these kinds of labels, right? And this is done uniformly at random. And so you'd have like all these labels kind of shoveled around. And so you'd very easily get false facts like, all mammals are cats. And then we also considered fictional ontologies, where we wanted to control for when the model doesn't know anything about these facts from the pre-training. And in those cases, we just replace the names of the concepts, like cats and mammals, with fictional words like wumpuses and bumpuses.
Mm-hmm. Thank you. Okay, we have just a couple of minutes left. Clarification on the previous question. So the question was concerning the number of tokens in output threshold. Could substitution play a role? And substitution is several steps of thought summarized in fewer steps by the model.
Oh, I see. Yes, yeah. So this was back referring to these experiments here. That's a good question. I don't know. I think you have to try it. We just kind of gave the problems to these large reasoning models and had them do their own thing, right? And just see like if their own kind of long chain of thought processes could find the answer. And to be clear, like the length of the context was not the problem, right? The number of tokens here are well below the maximum, which is, I believe, 32K for even the smallest of these models. So it wasn't running into any issues with the number of tokens hitting that limit, right? But it may still be possible, even in the case that having some sort of like summarizations, like intermediate summarizations within the chain of thought might improve performance. That's a good question. Yeah, that's something that you'd have to try experimentally. I'm not entirely sure.
All right. Well, we're at time, and as we predicted, a flood of questions for Abu. Great topic, great talk. Thanks, Abu. I'll just ask one final one. Many people saw the Apple paper. It was in the news quite a lot. So, and you did a more thorough analysis to make sure that certain things could have been explaining the problems that they showed, that to eliminate those factors. So, but would you say that overall, essentially, you confirmed their qualitative conclusions, just and making sure that there aren't confounders?
Yeah, I would say so. I think a lot of our observations kind of line up with what their high-level conclusions are. Yeah, like you saw this like very clear gap between. I can show you in the slide, this one slide, real quick. Like at the Apple paper, you saw this kind of gap between like the non-reasoning models and the reasoning models, but then they both kind of struggled at very complex examples. And you see the same kind of gap in our experiments, where you have these non-reasoning models kind of really do badly with very not very complex examples, and the reasoning models take a bit longer, but they also kind of drop off after a certain amount of time. So we see the very similar qualitative results and conclusions. Yeah.
All right, excellent. And you left us with a teaser, Abu, about what we can learn from this to actually make large reasoning models do better reasoning. So with your curriculum training, so we'll have you back perhaps once you have that out. So So thanks everyone. So the conversation continues. So any questions that weren't answered, and you can keep asking them on Discord. Abu, as you have a chance, maybe you can jump on Discord, answer any questions that are left there or that appear there in the near future. So, and look on Discord for the papers for the next presentation. This is a reading group style, so we try to announce the papers so you can read them in advance. All right, and this will include the famous DeepSeek paper. So many people, I think, will find that interesting. Thanks so much, Abu. See you next time. Thanks, everyone.
Thank you, guys.